In dealing with inverse trig functions, it's important to remember what the domain and range of that inverse trig function are and how they can be found by looking at the original function. So if we look at sine x looks approximately like that. And if we talk about the inverse function, inverse sine of x, we need to talk about something that's actually a function. It's going to be an inverse function. So in order to get the inverse of sine to be a function, we end up needing to restrict the domain of the sine function from negative pi over 2 to pi over 2. This restriction allows us to still get every single range value of the sine from -1 to 1 across a single continuous piece of the domain. So when we talk about the sine function, in order to find inverse sine, we restrict it so that its domain is negative pi over 2 to pi over 2, but still contains the range of -1 to 1. And that tells us that the inverse function, in this case, inverse sine of x, or what we've labeled as g of x, must have a domain of -1 to 1 and a range of negative pi over 2 to pi over 2. And since sine x is differentiable on this interval, its inverse, the inverse sine of x, should be differentiable on its domain, -1 to 1. So let's see if we can figure out how to actually take the derivative of the inverse sine of x. First step is going to be to write this as y equals the inverse sine of x, and then to take the sine of both sides of this equation. On the left-hand side, we still have just sine y, but on the right-hand side, the sine of the inverse sine of x is equal to x. And now we're going to proceed by taking the derivative with respect to x on both sides of this and find dy dx implicitly. So the derivative of the sine of y with respect to x is the cosine of y times dy dx. And the derivative of x is just 1. This leaves us with dy dx equals 1 over the cosine of y. So we found the derivative, but it's in terms of y. And our original equation, our original function, was in terms of x. So we'd really like our derivative to be in the same variable that we started in. Well, to figure out what the cosine of y is, we can use a quick little trick by recognizing that if y equals the inverse sine of x, as we said before, the sine of y must equal x. So we'll draw a right triangle, label an angle, the non-right angle, as y. And since the sine of y is equal to opposite over hypotenuse, that gives us the opposite leg is x, and the hypotenuse is 1. Using just a little bit of the Pythagorean theorem here, we can say that this adjacent side, we'll call it a, can be found by using a squared plus x squared equals 1 squared, or that a squared is 1 minus x squared, or that a is the square root of 1 minus x squared. And since the cosine of y is the adjacent side divided by the hypotenuse, we end up with 1 over root 1 minus x squared. And this is the derivative of the inverse sine of x. Just like all of our other derivative rules, the chain rule can be applied within. So if I wanted to find the derivative of the inverse sine of a function, u, we would just say this is equal to 1 over the square root of 1 minus u squared times the derivative of u with respect to x. So it's the derivative of inverse sine evaluated at u times the derivative of u in terms of x. And this is just an application of the chain rule for inverse trig functions. We'll see a bunch of examples of this in a minute. The other 5 inverse trig functions derivatives can be found in basically the same manner that we found the one for the inverse sine of x. So rather than prove them all, I'm just going to provide you guys with the formulas. These are the formulas of each of the inverse trig functions. One important thing to note that if you can remember the inverse sine, the inverse tangent, and the inverse secant rules, you'll notice that the co-functions of each, the cosine, just has a negative out in front. The cotangent is the same as the tangent, except with a negative out in front, and the cosecant is the same as the secant, except with a negative sign out in front. So each of the regular inverse trig functions, sine, tangent, and secant, if you memorize those 3, you can remember that the co-functions have derivatives with a negative sign out in front, but otherwise they're the same. In order to find the derivative of the inverse sine of the square root of x, we have to use the chain rule. We'll rewrite the problem as y equals the inverse sine of u with u equal to root x. The derivative of the inverse sine of u is the rule we learned. Should be 1 over the square root of 1 minus u squared. And since u is root x, we'll write root x squared. Then we'll multiply that using the chain rule by the derivative of root x, which is 1 over 2 root x, another rule you should have memorized. First fraction simplifies to 1 over the square root of 1 minus x, and the second one is just 1 over 2 root x. So we'll rewrite it as 1 over 2 root x times root 1 minus x. To find the derivative of the inverse tangent of x squared, well, again, use the chain rule. We write that as y equals the inverse tangent of u with u equal to x squared. We learned the derivative of inverse tangent of u is 1 over 1 plus u squared, where u is x squared. And then we'll multiply that by the derivative of u, which is 2x, resulting in 2x over 1 plus x to the 4th power. To find the derivative of the inverse secant of the square root of x squared minus 1, we'll need to use the chain rule with y equal to the inverse secant of u, where u is equal to the square root of x squared minus 1. Because the square root of x squared minus 1 also requires the chain rule, we'll rewrite this as u equals the square root of v, with v equal to x squared minus 1. Then we'll need to take the derivative of y equals inverse secant u equals root v, and v equals x squared minus 1, and multiply each one together. The derivative of inverse secant of u is 1 over the absolute value of u times the square root of u squared minus 1. The derivative of root v is 1 over 2 root v, and the derivative of v is just 2x. As we replace all the u's and v's with their respective terms, we can also cancel out the 2 in the numerator with the 2 in the denominator, which will then leave us with x in the numerator over the absolute value of u, which is the absolute value of the square root of x squared minus 1, times the square root of u squared minus 1. U is the square root of x squared minus 1, so u squared is just x squared minus 1, and then minus 1. Also, we'll have a square root of v in the denominator, which is the square root of x squared minus 1. We can then eliminate the absolute value on the radical x squared minus 1 because the square root is always going to be greater than or equal to 0. So the square root of x squared minus 1 times the square root of x squared minus 1 is just x squared minus 1. And we'll multiply it by the square root of x squared minus 1, or x squared minus 2. And this is our final result. If you want to factor x squared minus 1 into x plus 1 times x minus 1, you can, but it's not necessary. To find the derivative of inverse tangent of sine 2x, we'll rewrite it as y equals inverse tangent of u, with u equal to sine 2x. Since u equals sine 2x requires the chain rule to differentiate it, we'll rewrite it as u equals sine v, with v equal to 2x. Then we'll take the derivative of each of these three terms with respect to their variables, u, v, and x, and then multiply the results together. dy du is 1 over 1 plus u squared. The derivative of u with respect to v is just cosine v, and the derivative of v with respect to x is just 2. Replacing the u and the v results in 2 cosine 2x over 1 plus sine squared 2x. And that's our final derivative. To find the derivative of x arc cosine root 4x plus 1, we'll have to use the product rule, where the first function is x and the second function is arc cosine root 4x plus 1. The product rule says u times the derivative of v, so that will be x times the derivative of the inverse cosine of root 4x plus 1. The inverse cosine of root 4x plus 1 has to be differentiated using the chain rule. V is equal to arc cosine of w, with w equal to the square root of 4x plus 1. The square root of 4x plus 1 will be differentiated also using the chain rule, with w equal to root a, where a is equal to 4x plus 1. So to find the derivative of arc cosine root 4x plus 1, we will find the derivative of v, w, and a and multiply the results together. The derivative of inverse cosine of w, or arc cosine of w, is negative 1 over the square root of 1 minus w squared. The derivative of w with respect to a is 1 over 2 root a, and the derivative of a with respect to x is just 4. Then we will add to that the derivative of u, which is 1, times v, which is just arc cosine root 4x plus 1. The second half of this, the arc cosine root 4x plus 1, doesn't need to be simplified at all. The first part of it does. First off, 4 and the 2 will cancel out and give us a 2 in the numerator with this x. So we'll have a negative 2x in the numerator. And in the denominator, we'll have the square root of 1 minus w squared. W is root 4x plus 1, so w squared is just 4x plus 1. Make sure that that goes into parentheses. Then we also have the square root of a, which is the square root of 4x plus 1. As we distribute the minus sign, this becomes the square root of negative 4x. 1 minus 4x minus 1 just becomes negative 4x. So we now have negative 2x over square root of negative 4x, square root of 4x plus 1, plus the arc cosine of root 4x plus 1. If we simplify the square root of negative 4x, we can pull the 4 out of the square root, and it becomes a 2 outside the radical, which will cancel with the 2 in the numerator. And we're left with a final answer of negative x over root negative x root 4x plus 1 plus arc cosine of root 4x plus 1. And this is our final answer. To find the derivative of arctangent x over x squared plus 1, we'll have to use the quotient rule since it is a quotient of two functions, u over v. Quotient rule says the derivative is the denominator times the derivative of the numerator, and the derivative of arctangent is 1 over 1 plus x squared. So v du minus u times dv, which is just 2x, all over x squared plus 1, the denominator, squared. X squared plus 1 times 1 divided by 1 plus x squared cancels to just become 1. And we end up with a final result of 1 minus 2x arctangent x all over x squared plus 1 squared. To find the derivative of the square root of inverse secant of 3x, we'll use the chain rule with y equal to root u, where u is the inverse secant of 3x. Since the inverse secant of 3x has to be differentiated using the chain rule, we'll rewrite this as u is equal to the inverse secant of v, with v equal to 3x. And in order to find the final derivative, we'll take the derivatives of y, u, and v with respect to u, v, and x, and then multiply them all together. dy du is 1 over 2 root u. The derivative of inverse secant of v is 1 over the absolute value of v times the square root of v squared minus 1. And the derivative of v is just 3. So replacing the u's and v's with their respective values gives us 3 over 2 times the square root of the inverse secant of 3x times the absolute value of 3x, that being v, times the square root of 3x, the quantity 3x, squared, or 9x squared, minus 1. The 3 inside the absolute value can cancel with the 3 in the numerator, and our final result should be 1 over 2 root inverse secant 3x times absolute value of x times root 9x squared minus 1.